we have now finished all of our information for exam 1 and moving on to our exam 2 problems. So with this, we are going to introduce the idea of work and energy. So our first example is really just playing with these different new concepts that we just learned. And for it, we have a shell that I'm going to draw a little nice conch shell. I don't know, something like that. That is 1 kilogram in mass, 1 kilogram. And this shell is found by a little girl on the beach. Apparently very little, she's basically the size of the shell. And she's going to pick it up, and she's going to carry it up to the top of this cliff. And at the top of the cliff, she's going to take the shell and she's going to go ahead and drop it. We'll use green. So she's got the shell. And she's going to drop that shell. And that shell will drop and drop all the way until it hits the ground. And we'll go ahead and show it hitting the ground down here. So we've got our conch shell. This is not an art class, I'm sorry. And we are asked for a few different conditions. We are first asked, this girl is going to take this all the way up this 20-meter tall hill. So she is going from a condition of 0, which is the bottom, all the way up to the top of the hill where she's dropping it from. And we will call this condition 1, which is that top right before it's dropped. So our first what to find, I'm going to put them down here at the bottom of the board. We have our what to finds. The first one is going to be what is work done by the girl. And we can go ahead and call that the work between condition 0 and 1. So how much work was done between the shell being at the bottom and the shell being at the top? Next thing we are asked to find is our potential energy at the top. This is a physics video, not an English video. If I want A and T for at to have a space between them, that is my own initiative. I apologize. Potential energy, and at the top, we said top was condition 1, so we want to find the potential energy at condition 1. Next thing we're asked to do is right before it hits the bottom, it's got some kinetic energy. It's moving very fast. So I want to find my kinetic energy. And we won't put a space between it this time. At the bottom, which is going to be Ke at, ooh, I didn't label this guy. We're going to call this guy time 2. So kinetic energy at 2. And we also want the velocity. It's probably more than enough space, but velocity is not a W. Velocity at time 2. Was our velocity right before it hits the ground. Okay, which leads us to our final piece that we're after, and we are after what happens halfway down in the middle here. we've got our conch shell. Instead of at 20 meters or at 0 meters, our conch shell is now at 10 meters up. So kinetic and potential energy at halfway. So we have kinetic energy, and I will go ahead and call this guy times 3. Kinetic energy at 3. And we have potential energy at 3. And the last thing that I want is I'm also going to ask for the velocity at 3. I'm going to find all of those different pieces. That's a lot. Let's get started. My first one is pink. I'm going from 0 to 1, and I want to know how much work is happening. Well, we just introduced a new equation for work. We said work is equal to our force times our distance, and we said there could be a cosine theta in there, but that is really just saying we want our force and our distance, and we want them to be parallel. So in this case, the force, the distance we're traveling is from the bottom to the top. So I know she's bringing it up this little funky slope. It's not perfectly vertical. The distance traveled is from bottom to top, so we want just that vertical force because that's what is impacting this. So we already know, we've been finding force all through exam 1. So I'm going to start with my free body diagram. My free body diagram, I have downwards my weight of my thing, mass times gravity, and upwards I have my force by this little girl carrying it up. That is a really bad conch shell. I apologize. You try drawing with these markers. Good luck. Okay, with that, in order to solve that, I've done this a ton of different times. I'm just going to put it underneath here. I've got my sum of my forces in my y. I'll go ahead and call this my positive direction. So my forces in my y is mass times acceleration. Okay, in order to get this thing moving, in order to move it, we need to have whatever that acceleration is, kind of. In this case, we don't, because, well, in really most cases we don't, because we are moving and we're interested in moving it at an average rate. This is saying that we are using the average force and the average distance. And the average force and average distance, this is 0 acceleration. This is a constant velocity. We're assuming that she is moving it perfectly straight up the hill. So the force, any force over 0, any acceleration over 0 is going to make it move up, so we can say that that's how this is going to work. So our forces in our y, we have our upwards force of the girl, downwards mass times gravity, our weight, is equal to 0. Force of the girl is going to be equal to mass times gravity, which is going to be equal to 1 kilogram. That's the weight of this guy. We have it right there. Times our acceleration gravity, 9.81 meters per second squared. That comes out to 9.81 newtons. Simple enough, hopefully. That is our review portion. We now want this force to come up here, and our force parallel to our distance. Our distance is 20 meters straight up. Our force is 9.81 newtons straight up. We end up with a value of 196.2 Newton meters, which is 196.2 kilograms times meters per second squared. That's a Newton times meters, which would be the same as kilogram meters squared per second squared, which is the same as joules. So work between 0 and 1, because we're going from condition 0 to condition 1, is 196.2 joules. Let's see if I can do this without pausing. Perfect. Racing nicely there. Okay, that is our first what to find done. Let's move to the second. I'm going to go ahead and erase this guy just because it's right in front of my face. Potential energy at the top. Well, that's easy. I have a potential energy equation. That's one of our new equations. Potential energy at the top at 1 is equal to mass times gravity times height at 1. That's my potential energy equation. My mass is 1 kilogram. My gravitational constant is 9.81 meters per second squared. My height is 20 meters. Surprise, surprise. That comes out to 196.2 joules. Kilogram meters squared per second squared, joule. So 196.2 joules. Those two numbers sure look exactly, can't do it without putting my finger in the way. They look exactly the same, and that is a good thing, because if we think about our other equation that was new, we said our sum of our energies at 1 plus our work in, let's use my numbers here. Energies at 0, work from 0 to 1 is going to be the sum of my energies at 1. Potential energy at 0. H is 0. Height is 0, so no potential energy. Kinetic energy at 0. I'm not moving. Kinetic energy is 0. Work 0 to 1. That is 196.2 from our first part of our problem. Potential energy at 1. That's what we're trying to solve for. Kinetic energy at 1. We're not moving. Velocity is 0 at this point. We have no movement. That goes away. Look at that. Same thing. That's going to happen a lot today. Okay, that is our second part of the problem. I'd say halfway, but we get a little bit more complicated as we go. We've got half of our pieces answered. Okay, part 3. We're going to go ahead and start with that handy equation that we just had, and I'm going to write it out in the potential energy, kinetic energy form instead of in the energy form. And I'm going to go ahead and start at 1 and go to 2. So potential energy at 1 plus kinetic energy at 1 plus work from 1 to 2 is going to be the potential energy at 2 plus the kinetic energy at 2. Potential energy at 1. I have that right there. This is 196.2 joules. Kinetic energy at 1, it's not moving yet. Kinetic energy is 0. Work from 1 to 2. There's work done from 0 to 1, but there's no work between 1 and 2. So work from 1 to 2 is also 0. Potential energy at 2, we're back on the ground. Height is 0. Potential energy at 2 is 0. And that leaves kinetic energy 2, which is what we're trying to solve for. Hopefully at this point we're not surprising anyone by saying it is exactly the same. Okay, with that, next thing we're asked, well actually before I do that, let's say I want to talk about between 0 and 2. Well, between 0 and 2, I'd write potential energy at 0 plus kinetic energy at 0 plus work from 0 to 2 is going to be equal to potential energy at 2 plus kinetic energy at 2. I already know the potential energy at 2 is 0. We cross that out right above us. Kinetic energy at 0, we're at the ground, we're just sitting there, we have no velocity, so kinetic energy is 0, we're on the ground, potential energy is 0. Work from 0 to 2 is kinetic energy. The work that happens all the way from 0 to 2 is the same as the work that happens between 0 and 1, because we've got a work of 196.2 joules here is equal to KE2. Okay. We've got the work there and our work there. Our work here is 0. Our work here is 196.2. Our work here is 0. So that is canceling itself out, and we can solve the same thing that way. Don't really need to. I tend to try to avoid work when I can. It's a great quote for you guys to have on video. Okay, our velocity portion of this. Kinetic energy, we can convert to velocity because kinetic energy is associated with velocity. Kinetic energy, we have the equation 1/2 mass times velocity squared. So in this case, we know my kinetic energy at 2 is 196.2 is equal to 1/2 joules times 1/2 times 1 kilogram times velocity at 2 squared. Great. 196.2, this is going to be times 2 divided by 1, square root of that. So joules divided by kilograms is meters squared per second squared. Square root of meters squared per second squared is going to be meters per second. Units all work out. So we get velocity 2. If I plug all this into a calculator, I should get a velocity of 19.81 meters per second. Simple as that. 19.81 meters per second. Okay, let's stay on this one for a second because we had another way of finding that guy out. And that is going back to exam 1, we have our kinematic equations. So the one that is easiest to work with here is going to be my least favorite of them, but V2 squared is going to be equal to V1 squared plus 2 times acceleration times, well, normally this would be x or y. I'm going to call it h for height. h2 minus h1. I could write x there. I could write y there. Probably should have written y there, but I'm calling it h for this case. It's just choice of letter at this point. Velocity at 1 is 0. So I've got 2 times my acceleration. Acceleration of gravity is 9.81 meters per second squared. Technically, this is negative because I'm going to go ahead and call, whoops, it's going down. I'm going to go ahead and call up positive because that's what we normally consider to be positive. Times h2 minus h1. h2 is h2 is 0 minus 20 meters is my initial height, is going to be equal to velocity 2 squared Thankfully, our negatives cancel out because we can't find the square root of a negative number without imaginary numbers. We've got the square root of 2 times 9.81 times 20, or 2 times negative 9.81 times negative 20. That is going to give us 19.81 meters per second. And then if I wanted to do that, I could then say that kinetic energy is going to be equal to 1/2 mv squared. I have my velocity, I square it. I'm going to come out with the same kinetic energy because we use this equation to get from here to here. If we already have this and that's the same, going backwards is definitely going to give us the same number as well. Okay. Hopefully that was of some interest to you. Let's get to the last piece, and my cap has already fallen off of this one. Halfway. How do I want to do halfway? I can start a lot of different places. I'm going to go ahead and start with my potential energy. Because potential energy is an easy equation. So I want to know my potential energy at 3. Potential energy at 3 is going to be equal to my mass times gravitational constant times my height at 3. So that is going to be 1 kilogram times 9.81 meters per second squared times 20 meters. Whoops, not 20 meters. Halfway up, 10 meters. Saved myself having to make a video annotation on that one. So 1 times 9.81 times 10 is going to be 98.1 joules. Okay? Now I can choose any of my other numbers. So I'm currently working on number 3. I want to know it compared to any of my other numbers in order to determine, in order to fill out my big energy equation. So I am going to go between 1 and 3 because that seems fairly common sense to me. So potential energy at 1 plus kinetic energy at 1 plus work between 1 and 3. I know this should probably be 2.5 because it happens between 1 and 2, but it's just a subscript. Potential energy, oops, really can't use my finger like I can do on a chalkboard. Potential energy at 3 plus kinetic energy at 3. Potential energy at 1, I have right here, 196.2 newtons, or newtons, joules. I'm still on exam 1 questions in my head. Kinetic energy, at 1 we're not moving, so 0. Work between 1 and 3. There's nothing, there's no forces acting on it there other than gravity. Potential energy at 3, I've got that right there, 98.1 joules plus kinetic energy at 3. And I can subtract that 98.1 from my 196.2, and that is going to give me a value of, should have this. Yeah, it's just half. 98.1 joules is equal to my kinetic energy at 3. Kinetic energy is exactly half of what it was. So I can write both of these down now as 98.1 joules and 98.1 joules. Half of my potential energy has been converted into kinetic energy. And then my last piece I'm asked for is the velocity. Let's get that done so we can call it a video. Kinetic energy at 3 is equal to 1/2 mass times velocity at 3 squared. And kinetic energy is 98.1 joules. 1/2 mass is 1 kilogram. velocity at 3 squared. So I divide 198.1 divided by 1/2 and divided by 1. That's going to be 196.2. Find the square root of that. I cannot do that one in my head. And that should come out to 14 meters per second, more or less on the dot. 14.0 is what I have right here. Looks like I'm still mostly on the board. Yep, 14.0 meters per second. So note that kinetic energy and potential energy are halved because we're halfway down. The velocity is increasing exponentially because our kinematic equation is at squared. Well, not entirely that, but still, we have a velocity of 14 meters per second so far on the way down. So with that, we have our solution. Note for this guy right here, really hope that's actually 14. Yep, that looks right, yeah. With this, we have our velocity, we have our potential energies. What I'm rambling about here is I did not have to choose between 1 and 3. I could have done between 0 and 3, in which case my potential energy goes away. I've got a work, because the work happened, the girl was lifting it up. The girl is a force outside of the system, so that impacts it. I could do between 3 and 2, in which case I would move my 3s over here, because the 3s happen before the 2. There's still no work, but at 2 I have a kinetic energy of 196.2, and it works out exactly the same. So we can choose any 2 statements, make sure we keep track of the work between them. That will become a little bit more important as we get a little bit later into this unit. That's the first of the 2 example problems. Take care.